the final day of CPM, and this first and last highlight talk of the conference. And Tomek here will talk about string synchronizing sets. So go ahead, Tomek, and take it away.
Thank you. So this is joint work with Dominic Kempa that I've been presenting originally at STOC last year. And I'll speak about synchronizing sets and how they can be used to achieve sublinear-time algorithm for BWT construction and an optimal data structure for answering a longest common extension queries. So BWT has already been defined in this conference. In this work, I'm going to focus on ordering suffixes. So we have a sorted list of all the suffixes. And before each suffix, we write down the preceding character. So for example, here we have a suffix of length 6, and the 7th last character of the string is written next to it. And I don't want to have any sentinel character, so I'm assuming that the character preceding the whole text, namely the suffix of length n, is simply the last character of the text. That's just because to make BWT over the same alphabet as the original string. And as we all know in this community, BWT is very useful in compression, namely when T is repetitive in some way, then BWT tends to have long runs of equal symbols, and this means that you can use much easier methods to compress BWT than you would need to compress T itself. And BWT can be inverted, so you can do it without loss of generality. And BWT is also a central component of many data structures, primarily the FM index. And these data structures can be used to solve various tasks in a very small, space-efficient way. And here is some list of those tasks. And this means that constructing BWT is a crucial crucial step of constructing those data structures. So back when BWT was invented, the best we could do for construction was just to actually sort the suffixes and write down BWT according to the definition. Back then, the state-of-the-art suffix sorting algorithm took n-log sigma time, and shortly afterward, Martin Farag-Colton improved the running time to linear by showing how to sort suffixes over general polynomially bounded integer alphabets. And the space was linear. So linear space and linear time may look like the end of the story. And for suffix sorting, it actually is, because to store the suffix array, to store the sorting permutation, you need n-log n bits. And those n-log n bits require linear space and linear time to construct. But for BWT, it's not the case, because both the input and the output take n-log sigma bits only. So you can hope for improvements in space and time. And in space, indeed, it has been done. So Hon and others at Fox 2003 managed to get optimal space, n-log sigma bits, which translates to n over log base sigma n machine words. And this was at the cost of a log sigma penalty in the running time. And this log sigma factor was subsequently removed by Jamal at STOC using a randomized algorithm, and then Ayan, Yakov, and Gonzalo made a deterministic counterpart at SODA 2017. So before our work, the state of the art was that the space complexity is optimal n-log sigma bits, but the running time was still linear in n, whereas reading the input would only take n over log base sigma n time. And our contribution in this area is to improve the running time while preserving the optimal space complexity. Our running time is n log sigma over square root log n, so ideally you would hope for n log sigma over log n, which is just n over log base sigma n, but we only shave the square root log n factor, not the full log n factor. And this picture of previous work becomes much simpler if you focus on alphabets of constant size. Then you have just 3 relevant works. Originally we had linear time and linear space. Then Hon and others managed to get n bits of space, so n over log n machine words. And our contribution is to shave a square root of log n factor from the running time. And here a natural question comes into your minds: why is it square root log n? Why cannot we shave the full log n factor? And it turns out that there is some good reason for that. Namely, any improvement to our algorithm already in the binary case would mean that you could count inversions faster. Currently, the state of the art is m over square root log m, n times square root log m, sorry, for length m permutation. That's an algorithm by Chan and Patrashku from SODA 10 years ago. And any improvement to our BWT construction algorithms would lead to improvement in this inversion counting algorithm. And the techniques behind inversion counting are actually the central tool in orthogonal range searching. So unless there is some breakthrough in orthogonal range searching, we cannot hope for better BWT construction, even in the binary case. So essentially, the bottleneck is now not in the pattern matching community, but more in the data structures community. And I will come back to BWT construction later in the talk, but let me also introduce the other result regarding LCE queries. So you've heard about LCE queries already yesterday during Shai's talk. So LCE queries ask for the length of the longest common prefixes of two suffixes of a given text that you can pre-process, you can build a data structure on top of. And in this example, we have an LCE query for positions 4 and 13. We look at the suffixes starting there, and we see that the 7 first characters match, why the 8 ones don't match, and that's why the answer for LCE is 7. And these LCE queries were implicitly introduced in late 1980s by Landau and Vyshkin in their works about approximate pattern matching in what is now known as the kangaroo method, but they are now useful all across stringology in discovery of repetitions, in constructing text indexes, and in many, many more applications. And in early days, the story about data structures supporting constant time LCE queries looked quite similar to BWT construction. Originally, the space complexity was linear, the construction time was n log sigma, and with faster suffix sorting algorithm, the construction time was brought down to linear already for polynomially bounded integer alphabets. And here, improvements on top of this came much later. So only 3 years ago, the group from Kyushu managed to get some improvements in the space complexity. They didn't give any explicit construction algorithm. Then an early version of the paper, an archived preprint of the paper, which is going to follow my talk at this CPM, implicitly gave some improved LCE data structures. Namely, it allows shaving square root log base sigma n factor both in the space complexity and in construction time. So this is square root of what we would ideally like to shave. And also the work of Biren-Sviga and Ares, which was the work that Shai was presenting yesterday, also implicitly gives a data structure in this model where the space complexity is optimal, n log sigma bits, or n over log base sigma n machine words, but they focused on a different model, so their construction algorithm is not so efficient. It's linear and randomized only, whereas we would like to hope for something sublinear in n. And here our contribution is a fully optimal data structure. So we have constant time, n log sigma bits of space, n over log base sigma n construction time, which is necessary both already to read the input, for example. So here the improvement upon the work of Biren-Sviga and others is just the construction time algorithm, but we managed to get fully optimal data structure. So unless you are going to measure your instance size in some more subtle way, using something more than just the alphabet size and the string length, then this is the end of the story for LCE queries. But given that this contribution is quite similar to what Shai talked about yesterday, in this talk, I'm going to focus on the BWT construction algorithm only. So let me start with some special case, which is a toy case. It's not very useful in practice or anything, but it will illustrate the methods we are using in the general case as well. So in this case, I'm assuming that T has what I call a planted synchronizing set. Namely, T will be a binary string, but there will be twos here and there. Namely, we will have n over tau twos, and they're going to be distributed so that the distance between two subsequent tools in the string is at most tau. So here you have a string for tau equal to 4. It has 7 tools, and the largest distance between those at positions 1 and 5 is 4. And you can think of tau being quite small up to log n, and it's not a coincidence that I'm using the same name tau as Shai did yesterday regarding tau partitioning sets. But we'll come to this slightly later on. So how can we use this planted synchronizing set? What could we do it when its tau is small? Well, it turns out that what you can do is you can efficiently construct what we call synchronizing suffixes, which are just suffixes starting with a 2. So here is a list of those suffixes, and what we would like to compute is this sparse suffix array essentially. So the sorted list of those suffixes, of course, represented by their starting positions. So what can we observe? Well, we can introduce some blocks. Namely, I will make a block starting with a 2 and ending just before the subsequent 2. And now you can see that suffixes starting with the same blocks are located adjacently on the sorted list of suffixes. And thus we'll treat those blocks as integers. Recall that tau is quite small, so you can treat each block as an integer. And then sort those integers to give them names consistent with this lexicographic order of the blocks. And now let's, instead of building the sparse suffix array of the original text, let's make an ordinary suffix array of the string of names. So here you can see the suffix array. And as we have already observed, the first characters represent the first blocks in the list of synchronizing suffixes. And it turns out that this property is not only valid for the first blocks, but also for the subsequent blocks. So whenever you have a tie, you can just look at the second block, and by comparing the names of those blocks, you can decide the order of the corresponding suffixes. And that just means that the ordinary suffix array of the string of names corresponds one-to-one to the sparse suffix array of the synchronizing suffixes. And for the ordinary suffix array, we can construct it efficiently in n over tau time, because we have linear time algorithms for suffix sorting already if the alphabets are big. So that's what we can do easily. And let's see how to apply this for Barrows-Wheeler transform. So here, this is a sorted list of suffixes of my sample string. And now let's partition them into groups based on what we call distinguishing prefixes, namely based on the prefixes going up until the first occurrence of a 2. So what we did already is we constructed the sorted order of this last block, the block of suffixes starting with a 2. And what we can get from that is kind of block level BWT. So before each such suffix, we can write down not only the preceding character, but also the whole preceding block. And this turns out to be useful to build the whole BWT using some kind of LF mapping. Namely, if you consider, for example, the block with distinguishing prefix 02, so suffixes starting with 02, then those suffixes are suffixes starting with a 2, shifted by 1 position. And among those suffixes starting with a 2, you need to select those for which the preceding character is 0. And then, just like in the properties of the LF mapping, the relative lexicographic order doesn't change. So what we need to do is we need to filter those suffixes which are preceded by 0 and copy the remaining part of the preceding block. And now we get the preceding blocks for suffixes with distinguishing prefix 02. And this principle can be exploited to fill this whole Barrows-Wheeler transform kind of block-based, block-level Barrows-Wheeler transform. So you can do it recursively for longer and longer prefixes, and for different prefixes. So 1, 2 gets from 2, and so on. This is not yet an efficient algorithm, of course, but it gives us some glimpse how the structure of the BWT works in these instances with a planted synchronizing set. And what we actually care about is not the whole preceding block, but only the last character preceding our suffixes. But we have what may look like messy graph of arrows on the left, and let's disentangle it and view it as a tree. So we started with suffixes with distinguishing prefix 2. These are what we sorted explicitly, and we wrote down the preceding block. And then we did the operation of selection based on the last character, and we trimmed this last character, and we did this recursively. And this gives such a tree. Sometimes there is no suffix ending with a given character, so the node is empty and the whole subtree is empty. And what we achieve, what we want from this tree is just the last character of each block, not the whole block, just the last character. And it turns out that this tree is something that is already known to our community, and it's called a wavelet tree. So we have this sequence. So we have this sequence here, and it's a sequence of variable length items. So it's not completely classic wavelet tree, but still a wavelet tree. And for wavelet trees, we have an efficient construction algorithm for 5 years already. Namely, we can shave square root log m from the construction time and log m from space, compared to the total number of bit size of items in the input sequence. It is not a coincidence that we shave square root log n factor in time and log n factor in space. Namely, we'll just use this wavelet tree construction algorithm as a black box, and this is the only bottleneck of our algorithm. So let me wrap up how the BWT can be constructed in this case of planted synchronizing sets. So first we get such a string, we partition into blocks and give names to the blocks by just sorting the blocks and treating them as integers. Then we use an ordinary suffix sorting algorithm for large alphabets to construct to all the suffixes of the names, of the sequence of names, the string of names. As we have seen, this corresponds to the sparse suffix array, and this gives us block level BWT for suffixes starting with a 2. Then we treat this sequence as an input to wavelet tree construction algorithm, and we build the wavelet tree. And now, as we have observed, the BWT is just a concatenation of node labels from this wavelet tree. So how can we construct the wavelet tree exactly? Well, we enumerate all the possible substrings, all the possible distinguishing prefixes, all the possible substrings which end in a 2 and don't contain any other 2. Since our tau is pretty small, the number of such substrings is 2 to the tau essentially, so we can afford enumerating them and sorting them graphically. And now, for each such distinguishing prefix, we need to identify the corresponding node in the wavelet tree. And given that this kind of corresponds to the LF mapping, we read the distinguishing prefix in the right to left order. So we start with a 2, and we follow from the root of the wavelet tree the path 1, 0 in this case to get to a node whose label we copy as the first chunk of the Barrows-Wheeler transform. And we proceed in a similar fashion for subsequent distinguishing prefixes, copying the labels of subsequent nodes of the Barrows-Wheeler transform in some order. And that's the whole algorithm in the case of strings with those 2s, the toy case. So let's see how to generalize this to arbitrary strings. So now we need to come up with some replacement of the set of positions where 2 started. And for this, we define a notion of synchronizing sets. This is quite similar to the partitioning sets from Schei's paper, and it's actually been inspired by this notion. It has slightly stronger properties. So you can think of also string synchronizing sets as a kind of next generation partitioning sets, which are a little bit easier to operate, and those differences turn out crucial for BWT construction, and also useful for LCE queries, but not crucial in that application. So the high-level properties are the same as for partitioning sets. So synchronizing sets should be small, locally consistent, and dense. So again, you have parameter tau, and small means that the size should be n over tau. Consistency means that the choice whether a position is in the synchronizing set or not should depend only on the local context. And unlike partitioning sets, we insist that this context is only a rightwards context. So that the decision whether to include si to s in S or not should depend only on the 2 tau characters following I. And the density means that at least one every tau characters should be chosen. And here is an example for tau equal 2. And also in the bottom line, you can see another interpretation of this notion of synchronizing sets. So to construct a synchronizing set, you need to come up with some substrings of length 2 tau, sorry. So here are 3 of them, 0, 0, 1, 0, 1, 0, 0, 1, and 1, 0, 1, 0. And the synchronizing set consists of positions when at least one of those starts. So these are the few positions which are underlined. So this interpretation gives local consistency for free, because we just chosen them based on those contexts of length 4 in this case. But you still need to work in order to select your substrings so that the number of occurrences is small in total and that you don't have big gaps between 2 subsequent synchronizing fragments. And again, this definition is still too good to be true because of periodic regions. Namely, if you have a string of all zeros, then you need to decide whether you choose a positions where 0, 0, 0, 0 occurs or not. If you do choose them, your set is no longer small. If you don't choose them, it's no longer dense. So we cannot live with this definition. We need to tweak it slightly. And we observe that this issue occurs only in the long periodic regions with periods which is small in terms compared to tau. So we relax the density condition so that you need to select one in every tau positions only if the period of something locally there is large enough. And here there is also some difference compared to partitioning set that you have if and only if here, not an if here. And that's useful, but I will completely ignore this in the talk because I will ignore the whole periodic case. And in the periodic case, we are using techniques which are quite well known to this community: maximal repetitions, also known as runs, Lindon roots, and so on. And in general, whenever you apply synchronizing sets, the rule of thumb is that if everything works for the non-periodic case, then it's likely that after some work, you will be able to make it work in the periodic case as well, without losing efficiency. So how to construct synchronizing sets? It's also similar to the construction of partitioning sets. I will also give just a mathematical construction, and it's going to be a randomized construction, even though in the paper we de-randomize it carefully. So to build a synchronizing set, we now focus on substring of length tau, and we order them in a random fashion. So it's not like graphic ordering, it's random ordering. So here you have 4 substring of length 2, and it's some random order. And now we inspect fragments of length 4, so 2 tau, and we choose a fragment of length 2 tau to be in the synchronizing set whenever its prefix or its suffix is smallest in this ordering. So for example, here, the smallest element in the ordering is 1, 0. So we include in the synchronizing set all the occurrences of length 4 substrings starting with a 0, like those 2, or ending with a 0, like this one. And then we proceed with the next smallest substring of length tau, which is 0, 1. But in this case, we don't need to add anything more because everything else contains 0, 1 as a middle substring. So it's no longer the case that the minimum is either the prefix or the suffix. And again, you can argue that with this construction, the probability that each element is chosen is 1 over tau. That's because unless something is periodic, you have many distinct length tau periodic substrings. And the kind of very technical contribution of our work is how to construct this string deterministically and efficiently. So you have linear time in general and n over tau time if tau is small. And this is very different from the construction that appears for partitioning sets. But on the other hand, we don't care about maintaining small space complexity. So how can this, so let me just conclude saying how can this be used? So again, the main way we can use this synchronizing set is that we can sort suffixes efficiently, synchronizing suffixes efficiently, and the principle is exactly the same. Now we don't have such a clean blocks. We need to give names to some slightly longer substrings. But again, the idea is that we construct some string of names, and the normal suffix array of the string of names coincides with the sparse suffix array of the synchronizing suffixes. And this gives us some part of the Barrow-Wheeler transform kind of block-based. And now the algorithm is the same. We construct a synchronizing set, give names, sort those names, sort the suffixes of names. And now, since we have some context to the right, the string we are using, the sequence we are using for wavelet tree is no longer the left context only, but it has both left context and right context. But we still construct the wavelet tree and copy appropriate nodes from the wavelet tree in appropriate order to derive the Barrow-Wheeler transform over string. So in this non-periodic case, the algorithm is exactly the same. In the periodic case, there are some more technical issues which are resolved in the paper. So to conclude, the contributions of our paper are first of all, the Sublinear-Time BWT Construction algorithm and optimal data structure for LCE queries. And both these contributions are achieved through synchronizing sets, which are similar but more powerful than partitioning sets. And there is some further work stemming from this research, some of it already addressed. So I told you that the lower bound for BWT construction works for the binary alphabet, but later we actually managed to get it to arbitrary alphabets. It's still not written down, but essentially, unless you improve upon counting inversions, either our running time or linear running time is optimal for every alphabet size, the minimum of the two. Secondly, it is still open, so use these techniques to construct more sophisticated objects like Lempel-Ziv parsing or the FM index. A third issue is that our construction algorithm is inherently not friendly to external memory model. That's because we enumerate all those distinguishing prefixes. There are 2 to the tau of them. When tau is reasonably small, like exponential in the machine word size, it's fine. But when you have very wide machine words, like in the external memory model, it no longer makes sense. And then another interesting problem is, well, for LCE queries, for example, we are done when it comes to NN sigma, but what about more subtle instance size measures like entropy or the number of runs in the Barrow-Wheeler transform? And finally, we wanted to evaluate practical applicability of the notion of synchronizing sets. And actually the Dortmund group implemented LCE queries based on this. And we have now a paper just accepted to ESA 2020 track P about this. So it will be online shortly because we have to de-anonymize the paper before putting it on archive. All right, so that's the end of my talk. Thank you very much for attention, and I'll be happy to answer some questions.
Yes, let's all unmute and